So, welcome back. I'm going to continue where I left off earlier today. I'm going to remind you briefly that we're looking in this part at the effective theory that corresponds to the standard model as a low energy effective theory, assuming that the underlying physics is weakly coupled and decouples. Therefore, the appropriate expansion for the effective Lagrangian is in powers of 1 over lambda. I should say that later on in the course, I will refine that further to give a better estimate for the various coefficients. But at the moment, the basic expansion is in powers of 1 over lambda. The notation that I went through, let me also remind you that there is no reason in principle to exclude charge conjugate fields. And so along the way, once in a while, such fields will show up. Okay? So, and Shubha explained earlier today how you can construct those charge conjugate fields. I'll mention them in a little bit. Okay, so where I left off was in considering the dimension 5 operators. And I want to walk through this a little bit slowly to explain to you how one finds such operators. I will not do that for higher dimensions. It gets increasingly more involved, not more complicated, more tedious. And so I will not do that. Okay, so how does one go about constructing, say, the dimension 5 operators for the standard model effective theory? So the operator general form has B scalars, F fermions, and D derivatives. I remind you that the gauge bosons are all buried inside the derivatives. So that's why they're not explicitly stated. I also remind you that in my case, phi will be the standard model doublet with the quantum numbers here listed. Or, if needed, it's charge conjugate. All right, so I want a dimension 5 operator. So using dimensional analysis, that means that B plus 3 halves F plus D equal to 5. So Shubha explained earlier why you have a 3 half here, why B is here, like that. The dimension must obey this linear relationship. Moreover, every fermion appears with another fermion. Otherwise, you violate Lorentz invariance and angular momentum and all sorts of things. Well, Lorentz invariance, Poincare invariance. And so F must be even. And since you have, and B, F, and D are all positive. So the only way you can satisfy this relationship with F even is if F is 0 or 2. Because if F happened to be 4, then you would have here 6 plus B plus F equal to D. And that's impossible because B and D are greater or equal than 0. And you already have 6. And so this equation, this Diophantine equation, can never be equal to 5. Okay? So F is 0 or 2. Okay. So let me consider them. And that's what one does. One does, one case at a time. This is not a good color. I'm going to write on the board. So let me take first the case F equal to 0. So there are no fermions. So I have an operator that has only scalars and derivatives. And by this equation, B plus D is equal to 5. So one or the other of these numbers must be odd, because the sum of two even numbers is even, and the sum of two odd numbers is even. So one of them is odd. So let's suppose that B is odd. Then I have an odd number of isoscalar doublets. either 1 or 3 or 5. It doesn't matter. I know there's a limitation. It cannot be more than 5. It's 1, 3, 5. But and this operator has to be gauge invariant. D doesn't carry an isospin number. And so, and when I talk weak isospin, I mean the SU2 gauge number. But out of these guys, you can never make a singlet. So this operator with odd number of B fields can never become a gauge singlet just because of the group theory. And therefore, it is forbidden by gauge invariance. The case where D is odd is even easier. So this doesn't work. D is odd. That doesn't work either because now you have this guy. Each of them carries a Lorentz index, mu, nu, alpha, whatever. And now you have an odd number of them. And no matter how you contract them, there will always be one left over. And so this operator would then be Lorentz variant, would not be a Lorentz invariant operator. And so it's disallowed, violates the symmetries. Thus disposing of the case f equal to 0. Our operator, if it exists, must have 2 fermions. So let's look at that case now. So now we have something that looks like this. And I'm going to erase the other 2 possibilities. So now, because f is equal to 2, b plus d is equal to 2 as well. From this equation, f is equal to 2, b plus d is equal to 2. So there are 3 cases, 2 and 0, 1 and 1, 0 and 1, and 2, sorry. And I'm going to consider them separately. So let's consider the case b equal to d equal to 1. Okay, this one here. Well, this is a little bit more complicated. So what do we have? We have 1 scalar isodoublet, 1 derivative, and 2 fermions. There are 2 possibilities. Either, I'm sorry, no possibility. There's 1 possibility. I want to maintain Lorentz invariant. So this guy has an index. Someplace else in the operator has to be an index. There is only 1 place that can show up in a gamma matrix. I cannot add any other field. I cannot add a derivative because D is 1. The only place it can show up is with a gamma matrix. So it must look like this. So to write that in the usual way, it's going to look like this. So these guys must have the same chirality. They must both be left or they must both be right. Okay? If they are left, they are isodoublets. And then you have 1, 2, 3 isodoublets from which you cannot make a singlet. Violates Lorentz invariance. This doesn't work. If you have 2 right guys, they're isosinglets. And now you have 1 isodoublet, of which you can now not make a gauge invariant object. And so by gauge invariance, this guy doesn't work. In fact, since these were the only 2 possibilities, B and D equal to 1, is disallowed, gone. So that's why it says there that it violates gauge and or Lorentz invariance. The violation of Lorentz invariance is if you decide not to put a gamma matrix here, then you have a dangling Lorentz index. You might, in that case, you can have a doublet, and a singlet. You can make a gauge invariant object, but you have a dangling Lorentz index. If this is a doublet and this is a singlet, this is left-handed, this is right-handed, there's no gamma matrix in here. Or there's 2 gamma matrices in there, it doesn't matter. And in other cases, you have a dangling Lorentz index. And so you violate Lorentz invariance. All right, the next case. B is equal to 0, D is equal to 2. There are no scalars now. And now I have D, D, psi, psi. Okay? So how can I make that a Lorentz and a gauge singlet? Well, I could contract these two guys. And then I have psi by psi. But in that case, one of these guys is left, and the other one is right. One is a doublet, the other isn't a doublet, and therefore this violates Lorentz gauge invariance. The other possibility is to have something like this. Applied, okay. The derivatives can be both hit one guy or the other guy or one each. It doesn't matter. The point here is, again, chirality and gauge invariant. Since these guys are, there's two gamma matrices, they have the same, they have opposite chiralities, either left or right guys. Sorry, one left, one right. And again, you have a doublet and singlet, or a singlet and a doublet, and this guy violates gauge invariance as well. It doesn't matter. The derivatives can hit both one guy or one each. It doesn't matter. The point is the chirality and the connection between left, right, and isodoublet, isosinglet. So now this is dead too. And we are left with one possibility, just one possibility. That is where B is equal to 2 and D is equal to 0. No more derivatives. Yes?
You could write and allow only one term, but that will be total derivative, right?
One what?
One allowed term you could write, but that will be total derivative.
Total
derivative.
Yeah, total derivatives I don't.
Concept, but yeah,
It doesn't. Those are not interesting.
but
No.
the gauge invariant term.
The gauge invariant.
That's
Yes,
the gauge
exactly. Yeah, I'm not looking at those. And so the winner is B is equal to 2, D is equal to 0. Ta-da! 2 fermions, 2 bosons, and no derivatives. So O must look like phi, phi, psi, psi. And here, I'm not going to go through all the possibilities. It's just going to take a while. So the only thing that's left over is this. 2 scalars, 2 leptons, where LC is the standard charge conjugate. And phi tilde is the standard charge conjugate of the scalar. And that's it. As Shubha mentioned earlier, this was originally discovered by Weinberg, and therefore it's often called the Weinberg operator. It's actually a class of operators because you can have a family index on each of the leptons, so it's a class of operators. And the other thing to notice is that you have an L and an L charge conjugate. This object violates lepton number by 2 units. It's a necessary lepton number violation. So if you include this in your Lagrangian, of which you're perfectly free to do, it satisfies all the local symmetries, you're tacitly assuming that the underlying physics in some way violates Lepton number. So this necessarily is a Lepton number violating operator. Now, what kind of new physics can generate this? Well, you saw some examples this morning. There are three possible ways of generating this object at tree level. They're called the seesaw, various versions of the seesaw mechanism. Cleverly called seesaw number 1, seesaw number 2, and seesaw number 3. But there are an infinite ways of generating this at loop level. And I will give an example of this later on in the course. This O5 has generated, for one, you would think, I mean, this is just one operator has generated so many papers. You would be astonished by this thing. It has thousands of papers have been written basically on the effects of this operator. And that's because of its connection with neutrino phenomenology. It generates neutrino Higgs couplings, but that's, we hardly we had such a hard time seeing one Higgs. We can't see any neutrinos. We just see their effects, right? And now we have, this is like, the blind leading the blind. So the fact that this operator generates this thing at the moment is an interesting fact, but it's not something that we can in any way probe with the current precision that we have. But when spontaneous symmetry breaking occurs, this guy gets a valve, this guy gets a valve, and what this generates is a term that's quadratic in the neutrino fields. These are the standard model neutrino fields, left-handed. The reason you can make a Lorentz invariant object is that you allow for the complex conjugates to occur. This is a Majorana term, a Majorana mass term, and it created, and it is that which has created so much interest. If you look at the models that generate this at tree level, then the Majorana mass that's produced is of this order, B over lambda. Well, V is the standard model vacuum expectation. I'm sorry. Should be V squared. It has a mass, so it has to have units of mass. So it's a constant times a V squared over lambda. I apologize. V squared, okay? So V squared over lambda. 1V from this guy, 1V from that guy, 1 over lambda, because it's a dimension 5 operator, and a coefficient. So since neutrino masses are teeny, either lambda is very large or C is very small. These are two possibilities. One likes to have rather natural coefficients, that is, coefficients that are not inexplicably small. One tends to think, and this is a prejudice, that very small coefficients are produced occur, if at all, for some reason. And there's no reason one can think for C to be very small. So people consider models where lambda is very large, 10 to the 15, 10 to the 16 GeV. But in addition to that, this operator violates Lepton number. And so it has a possibility of explaining the matter over antimatter abundance in the universe by a mechanism in which, by a rather complicated mechanism. So very early in the universe, this type of interactions, let's say the physics that generates this guy's underlying, generates a lepton asymmetry that is more leptons than anti-leptons. And then a standard model process that occurs around the symmetry breaking time, when the temperature of the universe dropped below 250 GeV, transforms that lepton asymmetry into the baryon asymmetry, and therefore we're here. Without that, we would not be here. And so an existential problem for us and for all the universe that we see, I think it's sufficient motivation for studying models such as this that explain it. Going through the whole phenomenology of this is super interesting, but that's another course. I mean, it takes another course to do that. So that's what we have. Any questions about the construction? Yes?
In online there is a question, does this operator also changes the physics of scaleron?
Change the?
Physics of the scaleron.
Oh, yeah. So, okay, that is yet another course. So the operator at the moment, this operator is a low energy operator. It talks, it interacts. Okay, there are many models. The model that the simplest model involves heavy right-handed neutrinos, and so in no way that type of new physics talks to the quarks and baryons. However, once you come to sufficiently low energies, there are processes, non-perturbative processes that are associated with a classical configuration, unstable classical configuration, the standard model called the sphaleron. And it is through the interaction of that configuration with the leptons and with the quarks, which is rather complex, that the lepton number is transferred into baryon number. Was that the question? Is he happy or she happy? Smiley face? Okay, I'm good. I can, okay, thank you. Okay. All right.
One can see.
What's that?
One can see.
Okay.
He can see us.
Oh, we cannot see them.
No.
Okay.
But he can see.
He can see me. Okay. I cannot hide. Okay. Dimension 6 operators. So in order to construct dimension 6 operators, you go through the same process. You write it like this. And now in this case, b plus 3/2 f plus d is equal to 6. F has to be even, can to be 0, 2, or 4. If f is larger than 4, say 6, this equation cannot be satisfied for non-negative b and d. And then you go patiently considering all the possibilities. You might say, this is very tedious. You'd be very right. It is very tedious. But you do it because it provides a window into new physics, and you want to try to understand new physics. And so you just do it. Right? Or in the best case scenario, a friend of yours does it. And then you don't have to do it, you just copy it, which is exactly what I'm going to do. The only thing to remember, another thing to remember is you're allowed to include charge conjugate fields. And the other thing to remember is that the field strength tensors, they can be written in terms quadratic in the derivatives, because the commutator of two covariant derivatives gives you a field strength tensor. Okay, so that's something to remember when doing the construction. Okay. Lastly, you eliminate these operators that coincide when on shell, and you get this rather uninspiring list of operators. And this is only the first slide. Okay? So they are listed in classes. These are guys that have 3 or more vector bosons. These are guys that have only scalars or derivatives of scalars. These are guys with 2 fermions and 3 scalars. 2 fermions, 2 scalars, and a derivative. 2 fermions. No, you can figure it out. Like that. Let me just mention that many of these operators you may have met in the sense that they produce effects that are regularly talked about, like the raw parameter or the oblique parameters, which are good probes or are good probes of new physics. In other operators here correspond to those that would alter the neutron electric dipole moment, they violate CP, such as this guy here at the bottom and this guy here in the middle. They violate CP, and they would contribute, especially this guy, to the neutron dipole moment. So the point here is that the effects of many of these guys can be severely constrained, and however, of many others, the effects are completely open. We don't know. It's an ongoing process to measure them. The last thing I want to measure for this slide is, as you see, there are little indices here, Q, R, P, T, and so all these things, those are, I remind you, are the family indices. So there is no prohibition here in mixing families. And you might say, well, wait a minute, that generates flavor-changing neutral currents, and that would be true. And therefore, the data from flavor-changing neutral currents limits the effect. It puts constraints on the coefficients of the corresponding operators. Okay. Right. The type of effects that their various operators involve are not evident because I haven't written them in the unitary gauge. I've written them in a general expression. When you write the Higgs field here, the Higgs doublet, as VEV plus H, where H is the physical Higgs field, then these operators take a rather more familiar form. And for example, this particular set of operators from here modify the coupling of the various fermions to the Z boson. This operator at the bottom here modifies the couplings of the quarks to the W boson. Okay, those are things. So I'm just displaying them in their gauge invariant form. In practice, when you're looking at the phenomenology of any one of these operators, you write it out in terms of a physical basis and see what you get. Okay. These operators, all of them, have many terms. Many terms. You expand them in all the terms. Each term produces a vertex. Each vertex can contribute to a Feynman graph, included in a cross-section, in a loop, whatever you want, doing the calculations in standard fashion with a new set of vertices. The other thing to remember here is that those vertices, many vertices might show up, but those that come from the same operator, the vertices, the coefficients of these vertices are all correlated. So this guy, for example, this term here, this is the field strength tensor for the gluon field. The field strength tensor for the gluon field, I'm going to write down. I'm just reminding you. So G mu nu has a term that goes like this, and then has a term that looks like this. G strong, F, A, B, C, G, mu, B. That is, has a term linear in the gluon fields, has a term quadratic in the gluon fields. So my friend here, Mr. Neutron electric dipole moment, friend here, has three field strengths. So we'll have terms cubic, quartic, quintic, and sextic, power 6, in the gluon field, whose coefficients are all correlated. It comes from this expression here on the board, right? Some of them have extra powers of GS, and they might come out with particular numerical coefficients. Those are not for you to change. The numerical coefficients are mandated by gauge invariance, and you cannot, you can change them, it's okay. But if you change them, you're violating gauge invariance. So those are fixed by gauge invariance. All right, so I already bored you with this. Let me bore you more with the other guys. Okay, these are the slew or 4 Fermi operators. Ta-da. In all, there are 59 operators, assuming only one family, that is ignoring the family numbers. I have not bothered nor will I bother, nor do I encourage you to bother, to count the operators when you include all possible family combinations. I think many summarizes the thing. I also did not include baryon number violating operators. And there's a good reason for that. There is no indication of baryon number violation. The latest data, I think, for the lifetime of the proton is 10 to the 32 years, 10 to the 31 years, which if you count, that is a long time. That means that the decay time of the proton is very long. The width is therefore very small. And that implies that any contribution to the width must be very small itself. These operators must then produce tiny, whiny, teeny, very small effects, which means that the scale, the lambda, that is associated with them must be very, 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 very large. And therefore, since there's no effects, I'm just an input. Okay? Here they're classified according to what shows up. These are all left-handed fermions. Here are only right-handed. Here's left-right. And here's another version of left-rights. I often will refer to these guys as a vector exchange, just because you have a gamma mu, and you can imagine a vector connecting this current with this other current. Okay, the same thing here. I'll call it vector exchange. The same thing here, vector exchange. That's not necessarily true. I mean, because of Pierce transforms, in some cases, these operators might be generated by scalars. Okay, but I will still often refer them in unguarded moments. I will refer them as vector exchange operators. And similarly, I may call these guys scalar, or in this particular case here, that is a sigma mu nu tensor exchanges. Okay, but just keep in mind that that's just a label. It doesn't necessarily imply, especially in this case, that this operator you should never consider, because we have not seen any antisymmetric tensor in nature, so why bother with this guy? In fact, this operator can be generated by other particles, more common particles, vectors, scalars, through a Pierce exchange. A good exercise, for those times that you cannot sleep, is to derive the B-violating operators. There are not that many, and gives you an idea of what possible, very high-scale new physics can produce at low energies that we might be able to probe in future experiments. All right. So, when you're trying to use this thing in a reaction, so what happens often is that Atlas or CMS decide that they're going to look at something else. 3 top final states, 7 big plus 7 big quarks or something like that. That might be somebody's thesis, might be something that the collaboration is interested for one reason or another. And then one of the things that they do often is they recruit a theorist like us to try to find out what kind of physics beyond the standard model would be probed and what kind of sensitivity to that new physics would come from their measurement. And so either you or the collaboration or your advisor finds a reaction of interest and to look at. And then the process is very straightforward. You find the dimension 6. I'm just using dimension 6 operators because most of the processes you will look at are affected by dimension 6 operators. You find those that contribute to the process of interest. You derive whatever relevant observables are needed, cross-sections, decay widths, whatever. And then you compare with experiment. And from it, you find deviations. And if not, you find limits that constrain the operators at hand. And then you repeat. At the moment, there's no discovery of deviations yet. So we're still doing this little circular thing. You might think that this is kind of rather uninspiring. That's because of the way I've described it. It's not that you just go and say, okay, now I'm going to look at reactions with one top. Okay, no effects, got my limits. Now I've got reactions with two tops. I'm going to like 3 tops, 4 tops. Gets more. There's a little bit more than that. There is some certain amount of prejudice, some certain amount of understanding of various possible physics underlying the standard model that might motivate the choice of one type of reaction over another, of one type of operators over others. So there is, it's not mechanical. Obtaining the limits is as doing any calculation. That is mechanical. Right? Finding what calculation to do, which is of interest, that is certainly not a mechanical thing. But still, we're very sad that no effects beyond the standard model have been detected. Okay, so now I'm going to briefly mention the yet higher dimensional operators. And in fact, you can go through the same, there's a point of why I'm mentioning them. You can go through the same process as with dimension 5 operators, dimension 6 operators, and you get these guys, 20. And this is kind of a pattern that repeats. The dimension 5 is 1, dimension 6 is 60. Dimension 7 is 20. Dimension 8 is very many. When the dimension 9, it's not very, very many, but just many. Okay? So the odd number, operators with odd number of dimensions seem to be less of them than you might expect. Why that happens, I don't know. What I also don't know, it's tantalizing, is that all 20 operators in this list violate B minus L. Why should that be the case? I have no idea. And okay, but it's just so. It depends crucially on the content, the low energy content of the standard model. If you imagine adding to the standard model a singlet scalar, just one singlet scalar, has no quantum numbers, just a scalar, boring. Then you can then write down dimension 7 operators that don't violate B minus L. That's really trivial. The only thing you have to do is take my previous list, and for each one of these guys, multiplied by the scalar. Each of these guys is gauge invariant, and I multiply by gauge invariant object, S, my scalar. And so I add one dimension, and they all become dimension 7. But the fact is that the standard model does not have a scalar like that. And so the dimension 7 operators that I'm listed here are the ones corresponding to the low energy physics being the standard model, and they all violate B minus L. But why bother? I've been telling you, larger dimension, lower effects. We're already having no effects with dimension 6, and now I'm telling you to go and look at dimension 7. Well, the reason is that this provides the not dimension 5 L violating operators that come up. There's also dimension 9 operators that violate L, but I will come to those in a minute. So because these are L violating and B minus L violating operators, they have a certain amount of interest. And then we come to the next frontier, operators of dimension more than 7. You can find, it's instructive to look at those papers. They have tables with lists of operators. I mean, and there's hundreds and hundreds and hundreds of operators in this thing, and they're all listed there. Um, and they're just listed. They're just lists. I guess they're written because the authors could do it, but to be honest, I don't see the point in going around and listing all operators. What I'm trying to say is don't think the fact that there's no dimension 10 operator list as an opportunity for research. This is not to do. The only reason you might consider operators with dimensions higher than 6, in fact, is because there are specific processes to which these guys contribute and to which no other one contributes. So they're targeted. And in that case, you're not interested in all operators of dimension 17, but just in the one guy that contributes to the one process of interest that you are looking at. Okay, so looking at trying to generate all of them, it's a demonstration power calculation of power and things like that. But in practical applications, you don't do that. You find the operators that are relevant for your process, and then you work with those. And this is the intent of this last comment here. When I look at my version of effective theory in neutrinoless double beta decay, I'll give an example. In that case, I will need a dimension 7 operator, and I will need a dimension 9 operator, but that will justify the need when I come to that time. And it's only one operator for each. There are software programs that very cleverly generate all the operators at any loop at any order that you might need. So now actually sitting down and writing them down becomes even more of a. I think people have better things to do now that we have computers to do that for us. Any questions? Okay, if not, let me start with the next topic. I have a few minutes, and talk about, start with applications. I will have some applications, then I'll go back to some formal talk about discussion on the properties of effective field theory, but I think it's good time to take a break of all these abstract things and look at some specific application of the formulas. There are many processes to which the effective theory operators contribute, many, of course, all of them. Okay? But in many cases, the problem we face is that the standard model produces a huge signal, and we're trying to find buried under it some effects of new physics. In principle, if we had enough statistics, that could be done. In practice, we don't have enough statistics. So what one tries to find are processes where the standard model is either absent or strongly suppressed, and where the effects of new physics can shine through without too much interference. And I'm going to show you one example to begin with here. So this is a rare standard model effect. I'm going to look at it. And I'm going to imagine that I have an E plus E minus collider. Now, I know we don't have any E plus E minus high energy colliders anymore, but we used to. So maybe in the future we will yet again have one. Okay. So this was a calculation done for LEP, the last large E plus E minus collider. It can be easily extended to planned colliders like CLIC or the ILC, but I will not do that. I will just give you the calculation for LEP. So imagine that you have an E plus E minus machine, and you're looking at processes where there are n B quarks in the final state, plus something else. X can be anything except no B quarks. And by B quarks, I mean B or B bar quarks. Just don't come think, just no B. Now, In the standard model, the third family mixes with the others, and there's a point for saying this. However, the mixing angles to the third family are small. These numbers might be updated. So these are relatively old numbers, but they will not change in order of magnitude. So the point is that in the standard model, the third generation almost does not mix. So, because of that, the number of quarks in the third generation does not change from initial to final state. In the initial state, I have no quarks at all. So in the final state, I will have to have an equal number of third generation quark anti-quark pairs. It can be B bar, B T bar, TB bar, and so on. Okay. I am going to assume also that I don't produce T quarks. That was true for the LEP calculation that I did because the LEP didn't have enough energy to produce a single T quark. So it just didn't happen. So in that situation, since I have no quarks here, and since quark of the third generation do not mix with the others, okay, to first order, to first approximation, setting these guys equal to 0, this number, little n, has to be even. I have to produce an equal number of B and B bar quarks. Once you include this, that's no longer true, because a B quark can oscillate into a C quark, and now you can have a B bar C in the final state, for example. But the amplitude for that is very small. It's suppressed by a CKM angle, so it's small. Okay. And that's the idea. The standard model cross-section for this, when n is odd, will be small. And so it allows the possibility, provides a window for probing violation of this approximate discrete symmetry of the standard model, approximate in the sense that it's broken explicitly by these angles. Probing that affects, new physics effects that might actually violate the symmetry relatively, without any suppression, I should say, relatively largely, strongly, without any such suppression. And that's the idea. So with that, there is this approximate symmetry, which is -1 to the number of B quarks. That has to be even for the process at hand. So each state, you can say it has ZB equal to 1 or -1, according to the number of B quarks in it. So this is what I just said. And so this process is in fact very rare in the standard model. And so new physics effects that violate this are easier to observe. And that sounds straightforward and everything. The reality is a little bit more complicated because even if the standard model cannot produce this at a significant rate, experimental error can certainly do it. So saying I have found n quarks of any one flavor is complicated. Within an experimental setup, there's an efficiency for identifying quarks, and which is not perfect. And there's also a probability for mistaking quarks of a different flavor as B quarks. And all that has to be taken into account. LEP was a fantastic machine. It operated for many years, and they understood the detectors at LEP very well. And so by the time the experiment matured, then all these probabilities that I'm telling you about were very well known. How much of chance you have of producing a C quark and having your software identified as a B quark, mistaking it for a B quark. The probability for that is known. Similarly, the probability for the other way, that you have a B quark and mistaking it for some other type of quark, the efficiency for finding a B quark, that was also known. And so on. and those kinds of effects could not be ignored. So if the probability of making mistakes were all zero, then it would be just straightforward calculation. I think otherwise you have to include those effects. Like this. So instead of considering simply producing n big quarks, I'm going to imagine I produce m c quarks and l light quarks. That means strange up or down quarks. Okay. Then the cross-section that you actually measure is a funny combination of all the ones for this production, for this final state, because you may screw up and misidentify a B quark, screw up and identify a C quark as a B, or identify a light quark as a B as well. And this thing is the cross-section then that you miss. This is the probability of actually identifying a B quark, U of them. Okay, U, V, and W are integers. U of them you identify correctly, N minus U of them you misidentify. V of these guys you mistake. And M minus V you don't mistake as V quarks. And similarly for the light quarks. And this is a combinatorial factor. And the sum is all this. And I just confused you a little bit more because I'm detecting KB jets instead of N, and I apologize. So I'm looking at final state where my software says you have found KB quarks. That is not that I have KB quarks. It has a certain chance of having different number of B quarks, less than K, but different number of actual B quarks, and mistaken C quarks and light quarks for B quarks. And you have to take all that into account. You do this, and this is the cross-section that you're interested in measuring and calculating. Any questions about this? This is a little bit too much phenomenology, but really, you really have to do this. Otherwise, the results, you just get results that are not taken seriously. They're not relevant for the experiment at hand. All right. Oops. And now we have errors and backgrounds. So this is let me call this NKJ, is the total number of events with KB jets and J total jets with K of. So this is calculated for this, it's that type of construction where N plus M plus L is equal to capital J. And if you want to have an exclusion limit on the type of new physics that might produce this violation that I'm talking about, you want this condition to have the prediction from the standard model minus the prediction of your theory, that is standard model plus effective theory, has to be 3 times larger than an error. This is the 3 sigma condition. This error is a sum of 3 errors. The easiest one is a statistical error. This is the square root of n error that you're familiar, hopefully, from statistics. So yeah, you put it in here, this contribution is n. I'm assuming that error and the others are uncorrelated, so they add in quadrature. The other term here is a systematic error. That is a problem of the experiment. Those were calculated by the experiment and told by us. These are not something a theoretician calculates. Just you need to know the experiment in detail. So this we get from lab. And that theoretical error has to do with effects that we did not take into account. QCD, these are quarks. So there are QCD effects to take into account, mainly. That's the main effect. And we parameterize that, a term linear in the number of particles, a number of events that number of events that we produce times some quantity delta t. I'm running out of time. I won't finish. So let me tell you what the new physics is, and then tell you what's going to happen, and then finish. So there are many operators in the list that I showed you that violate this ZB, many. And we chose one, a 4 Fermi operator, random. And this operator has the virtue that it has two leptons, in particular have an electron and a positron in one factor here. It has two quarks in the final state with flavor labels I and J. So what we did is we took I to be 1, that means the first family, or 2, and we took J to be from the third family. So this would violate this ZB symmetry because the operator has a single object in the third family by assuming this is in the first or second family. Okay? I think we took the first family. You might say, well, that's contrived. In a way it is. But what's what we're trying to prove? To probe types of new physics that generate violation of this ZB thing. Okay. There's plenty of physics that do this type, that generate this type of effect, and would generate this operator at low energies. And you might have noticed I forgot to put a C here. I did forget to put a C here. I apologize.
So
Yeah.
this operator has generated, you have written this, it is generated by a heavy electroquark.
I'm sorry?
This operator.
It can be generated by leptoquarks? Yes, certainly can be generated by leptoquarks. It can also be generated by Z prime with flavor-changing couplings.
So what is the source that it has?
Okay, the question is, what could generate this operator?
Yeah.
I could generate this operator. I'm going to write the things that can generate it at 3 level. Okay? So could generate, so what do you have? You have 2 leptons and 2 quarks coming in. Yeah, 1 quark and a quark. Yeah. So, for example, it can be generated by this type of diagram. Okay. The catch is that this vertex of the Z prime to the quarks must somehow violate flavor. It must have first generation here and third generation here. Okay? There are limits. There are limits on this type of coupling. Yeah, there's limits on flavor changing neutral currents. The limits involving the third generation are weaker because it's just harder to measure. Well, at the time. Now it's better with the various B experiments. But there's another one that you mentioned, of course, this. And this is less problematic in the sense that the only thing you have to do is assume that there is, remember, this is an E plus E minus collider. So this is first generation, and say first generation guy here, and this is first generation and third generation. So you have to assume you have a leptoquark. In this case, it has to be a vector leptoquark. So leptoquark that couples, as its name indicates, leptons to quarks, which also has flavor-changing couplings from one generation to the other. Okay, so those are the two possibilities. Once you allow the thing to be generated at loop level, the sky's the limit. There's many operators, there are many processes that generate this operator through loops. It's more complicated.
No, another point is like suppose we have written this operator in the mass basis.
In the
Mass basis.
in the mass region?
We have written this operator in the mass basis, right? In this operator, that is Q the quark only. This is not the doublet or
No, this is the doublet. These are all doublets. This is the standard. L,
yeah L for
L,
isodoublet.
I use the isodoublet. L is, in our case, electron, L, neutrino, electron. And quark is up left, down left. Quark left, down left. So this operator, in fact, generates in itself many vertices. Okay, so that would be, 4 vertices. It has a neutrino, quark has a electron. Okay, neutrino, up, neutrino, down, E plus, E minus, up, E plus, E minus, down. Yeah. Thank you. Other questions? Okay. I apologize for over.
Yeah, Jose.
Yes.
Why this leptoquark has to be vector boson?
A vector?
Why
Yes.
this?
Why does it have to be a vector boson?
Yeah, not scalar.
In order to get this operator, this operator looks like this. From a leptoquark, you would have to use a Fierce transform,
Yeah.
right? A Fierce transform. So this guy generates something like L bar times Q
Okay.
and a Q bar something L. If the leptoquark is a scalar, this is 1. If the leptoquark is a vector, this is gamma mu.
Yeah,
Okay?
got it.
And what happens is that when you do a Fierce transform, only the vector 1 will change left into left, that kind of thing. It's just it's a feature of the Fierce transform. Other questions? All right, thank you. I will see you tomorrow, and we can have tea, right?
Yes.
We have tea. All right. Thank you.